Welcome to lecture Flexible AC Transmission System and Power Quality. This is the second unit. The name of unit is Static Shunt Compensator. There are different type of there are different type of fact controller. One may be connected in shunt or series. Basically, the shunt compensator is a shunt compensator or shunt fact devices. It is a one kind of controller which controls the variable, or it provide the variable impedance or variable source, or the combination of these two. The principle of all shunt type of controller or the compensator is to inject the current into the system at the point of connection. Every variable, every shunt impedance connected to the line, it causes the variable current flow, and hence inject the current in the line. Either it may be an inductive current or capacitive current. When the current is capacitive, it is going to provide the reactive power to the transmission line, and when it is a compensator, it is going to provide the it is going to consume the reactive current. So the purpose of the reactive compensation is to change the natural characteristic of the transmission line, or we can say that to modify the electrical characteristic of existing transmission line to make it more compatible with the provide the demand of the load demand, and at the same time it will increase the power handling capacity of the existing transmission line, and it recognize that with the help of fact devices, it is possible to enhance the steady state and transient stability of the system. Now, the purpose of the reactive compensation is to change the electrical characteristic, which is we have just discussed. Thus, the shunt connected fixed or mechanical switch reactor are applied to minimize the line voltage under light load condition. So under light load condition, what happened? The voltage of the transmission line get increases. That is the surplus of reactive power. And because of the surplus of the reactive power, voltage profile get increased. To compensate or to consume that, we have to connect one reactor in parallel with the transmission line, which consume the reactive power, and hence it maintain the voltage profile of the transmission line. At the same time, under light load, at the heavy load condition, the voltage of the transmission line decreases. It means that there is a deficit of the reactive power, and that deficit of the reactive power can be compensated with the help of mechanically connected to some capacitor in parallel with the transmission line, and hence it is possible to improve the voltage of the transmission line. So here the shunt compensator, either it may be a capacitor may be connected, or also a reactor may be connected, and this may be a electronic control with some proper control. Then it become a shunt, it will become a shunt fact devices, or the fact devices which is connected into the transmission line. Okay, so here our learning objective is to understand the need of shunt compensator, which we have just discussed. Second is the best location of the shunt compensator, midpoint shunt compensator, and its active and reactive power equation along with the phasor diagram. So here the point which we have considered here as a understanding of need of shunt compensator. Need of compensator is to compensate the reactive power. Either it may be a surplus of reactive power, or it may be the deficit of the reactive power. Now, what is the best location? It is found that it is observed that the sag in the transmission line is maximum at the midpoint of the transmission line. So it is considered that the fact devices or shunt controller or shunt compensator can be connected at the center of transmission line. So for that purpose, we have one diagram, say midpoint voltage regulation for the segment. Say here for this we will consider a simple line to network to machine system. Say this is the machine 1. It is a generating station. It is connected with the lossless transmission line. Lossless transmission line means there is no resistance in the transmission line, and when there is a no resistance, there is a no power loss in the transmission line from sending end to the receiving end. Say this is Vs and this is Vr. This is our simply, this current is I and the reactance is X. Okay. And we have ignored here the capacitor of the transmission line and resistance of the transmission line. The power P is equal to Vs Vr upon the reactance is X, transfer reactance is X into sine delta. This is the P delta equation. Already we have learned into the machine 2 as a synchronous motor. Okay. Now, what is the phasor? What we can say that it is the power angle characteristic of the transmission line. This is the angle delta and this is the power P. Okay. So under such condition, it is able to draw the power angle curve. It is a sinusoidal equation. It's a sinusoidal curve, therefore, and this is nothing but here we will consider that Vs Vr, they are equal in magnitude and is equal to V for our simplicity. So this equation become V square upon X into sine delta. Sine delta. So this is V square upon X into sine delta. This is the equation. Now under such condition, when it become maximum, it is going to become maximum at delta is equal to pi by 2. That is a 90 degree. Delta is equal to pi by 2 and it is equal to pi, and the maximum power is equal to P maximum when delta is equal to 90 degree. This is the maximum power. Okay. Now let consider equation. Let consider the system which comprises of same thing, but we are going to connect one shunt compensator, and that compensator is an ideal compensator. So this is the reactance. It is connected in the center of the line. So the reactances get divided into the two part. One is the from sending end part, sending end segment, and second is the receiving end segment, and rest of the transmission line is as it is. Only this reactance become X upon 2. This reactance become X upon 2, and here we are connecting a shunt capacitor, shunt ideal compensator, isn't it? Ideal compensator. So it is a ideal compensator. Now at this point, it is a say voltage is Vm. This voltage is Vs, sending end voltage, and this is Vr. Okay. Let the current is will remain same, no doubt, but we can say that Is and this is the Ir is from the receiving end, isn't it? So let we will consider here the current is same. Vs is equal to Vm is equal to V is equal to some voltage V. Now what is the phasor diagram under such condition? Say this is the phasor diagram. We'll try to develop the phasor diagram. This is the midpoint voltage is Vm. Okay, somewhere it is receiving end sending end voltage Vs. Similarly here it is the receiving end voltage. No doubt their magnitude is same, Vr, and this part it is I into X upon 2, this much part. Okay, similar equal part in the two side. Now under such condition, the voltage, what would be the voltage? Sorry, what would be the angle? Total angle is delta, so it is a delta by 2, isn't it? It is a delta by 2. This angle is delta by 2. Let we have more some classification, more details. Here we have drawn one more voltage vector. Here one more voltage vector we have drawn, isn't it? So how much this one reactance? This reactance is X divided by 4. This also x divided by 4 multiplied by current is the voltage, and therefore this angle is delta by 4. This is quite somewhat difficult to understand, but try to understand. I am just elaborating it. This is the current I. Say this is the current of the transmission line, total current of the transmission line, and there it is providing some current which is equal to the which is in phase quadrature. Injected current should be a phase quadrature. As long as the injected current in phase quadrature with the line current, it is going to consume or it is going to supply the reactive power. Otherwise it will handle some active power also. And in ideal compensation we consume that the active power handled by the compensator is equal to the zero voltage, isn't it? Now this is delta by 4. Now suppose this is the voltage, some voltage is V voltage. We are considering this voltage V R is equal to, what is that voltage VR is equal to? Sorry, this voltage VRM. VR will write as a, this is voltage is any voltage, we'll give the name as VRM. So VRM is equal to, what would that value? It is equal to VR into, as this angle is delta by 4, so cos of delta by 4, and which is equal to, VRM is nothing but the V. So VRM is equal to voltage V into cos of delta by 4. This is one value we have found as a voltage at the one power tram. Now similarly the current which is flowing, it is IMR. So IMR multiplied by IMR multiplied by the reactance X divided by 4. So current multiplied by reactance, it is the magnitude of voltage. So this one, this is equal to it is equal to VR into sine delta by 4. So is equal to VR into sine delta by 4, which is equal to, VR is nothing but V. So V into sine delta by 4. Okay. So can we write IMR? So IMR is equal to, what is that? It is 4V upon X into sine delta by 4. What is the power? P is equal to multiplication of voltage and current, VMR, and this one. So it is equal to VRM and VMR. So it is V and V. So it is 4V square upon X, as it is sine delta by 2, sine delta by 4, delta by 4 into cos of delta by 4. Can we write this equation as, it is equal to 2V square upon X, which is remaining, 2 is remaining. So multiplied by twice sine delta by 4 into cos of delta by 4. Now twice delta by 4 into cos of delta by 4 is nothing but sine of delta by 2. So as per the quadratic equation, the power P is equal to twice V square upon X into sine delta by 2. So this is the equation. This is the equation. Now we want to compare this equation with respect to the two machine system, means the transmission line system as it is without any compensator. So this is the two transmission line, two source is there, or two machine system is there having reactance X. It is a lossless transmission line. Here it is a two machine system, lossless transmission line. Only the capacitor has been added. The power is equal to twice V square upon X into sine delta. Now Draw this power angle curve on the existing power angle curve of the two machine system. So it is also the sine curve, whereas it become a maximum, only when delta is equal to 180 degree. Delta is equal to 180 degree means sine 90, and it is equal to twice v square upon x is the maximum power. And see here, what is the maximum power? V square upon x is the maximum power. This much is the, so here P is equal to P maximum. P maximum is equal to V square upon x at delta is equal to 90. But from this equation, the maximum power is doubled. See here, it is V square upon x, it is twice V square upon x. So here the power handling capacity has been increased. At the same time, it become maximum at delta is equal to pi or 180 degree. So say if this is the 180 degree and the power become maximum at this point. So here the power become maximum at somewhere it is the P maximum under second case, say second case. But it is going to become maximum at this point. So what is our conclusion? Our conclusion or our observation is that without any compensator, the maximum power transmitted by the transmission line is V square upon x at the power become a maximum at delta is equal to 90, isn't it? Whereas with the help of midpoint compensator, the same transmission line can improve the power handling capacity by double, and at the same time the angle delta also get increases. So system will be stable. Here the system is stable only up to this one. The system is stable in this region. Okay, so the maximum stable angle is 90 degree, whereas by connecting the capacitor, the maximum stable angle become up to the 180 degree, and the maximum power also be the double. Now, as we know in the conservative criteria, which we have already done in the power system stability, we never operate our system to the calculated value, but we will operate our system much more smaller than the calculated value. So even though if you are going to operate here, the power handling capacity is quite good as compared to the without compensation. So with the compensation, the steady state stability can be improved, as we have a large amount of area or large amount of region or say margin is available for the transient condition. So the system stability is both, one is the steady state stability and second is the transient stability can be improved. And second, it is possible to increase the power handling capacity or power transmittable ability of the system can be improved with the help of midpoint compensator, isn't it? So our conclusion, our point to be remembered that in the lossless ideal or lossless transmission line, and if you are connecting ideal compensator for understanding purpose, the best location of the compensator is a midpoint one. Why it is midpoint one? Because the voltage sag at the midpoint is maximum or it's more, and therefore if you improve, if you are going to inject the current, either inject the current in phase quadrature with the line voltage, either it is going to supply the reactive power or it is going to consume the reactive power under capacitor connected or inductor connected respectively, and hence we can improve the transient stability, steady state stability and power handling capacity of the transmission line. And this is the main objective of the fact controller. Our objective of main fact controller is to modify the electrical characteristic of the existing transmission line to obtain the controllability, power handling, transmittable capability, as well as the steady state and transient state, or say simply stability of the system. Okay, so this is the system. Now we will consider with the help of given diagram. See here, the same points has been considered only with some proper way, because it is need to elaborate the equation over here. Again, the total transmission line reactance is divided into the two equal part, x upon 2, x upon 2. Current is there, and midpoint ideal compensator is connected to the midpoint, or say ideal compensator is connected to the midpoint, and whose voltage is Vm. So the same phasor diagram which we have considered, and by using this phasor diagram, the equation of power without any compensation, it is not given, because it is simply to very well to understand P is equal to V square upon X into sine delta, but with the help of compensator it is twice PV upon X into sine delta upon 2, isn't it? So this equation we have found. Now to obtain the double the power handling capacity, there is a cost of reactive power, means we have to provide the reactive power by the midpoint compensator, and the quantity of the reactive power also be the very high. So Q is equal to 4V upon X 1 minus cos of delta by T. So see with the help of phasor some diagram, this one. So with this one, this is the first power without any compensator. So you can say that without compensator, shunt compensator, isn't it? And this is the maximum power P maximum, whereas this curve is with compensation, with midpoint compensator, and with the help of midpoint compensator, the maximum power is going to double, twice the maximum. Here is the maximum, it is twice maximum, and we can say that the maximum power is going to occur at pi by 2 without any compensator, but with the help of compensator, the maximum power is going to become maximum. The maximum power is going to become at angle is equal to 180 degree, and the system is more stable. Here the system is stable up to the 90 degree. Here the system is going to increase. So here we can say that the steady state as well as the transient stability has been enhanced, and this is the quantity of reactive power needed to obtain the required value. So this is the some midpoint compensation. Now when this is the midpoint compensation is there, no doubt it is possible to divide multiple, or to obtain or to connect some multiple midpoint or say shunt compensation in the entire transmission line. Say for example, this is a transmission line, it is divided into the 4 part in equal 4 part. So here it is the sending end voltage Vs, okay, and here is the load receiving end voltage Vr, and no doubt we can connect a capacitor, we can connect the midpoint compensator. This is one, say different color, so we can connect a compensator, say one compensator, ideal compensator, second point, second compensator, third compensator, and so on. But when we are connecting the number of shunt compensator in the entire transmission line, it has to be synchronized, all the capacitor, all the shunt compensator to be synchronized very well, otherwise it does not give the proper operation, isn't it? Second, when we are doing such type of synchronized control, the cost of the system bed get increases. No doubt it will increase the calculated power or theoretical power is very large, but it is better to connect only one shunt compensator at the mid of the transmission line, which avoid the sag, which obtain the proper voltage and avoid the voltage collapse or voltage instability in the system. So it is today we'll stop here as a shunt compensator. Next time we will see the shunt compensator which is connected to the load end. It means that this is the transmission line, okay. Instead of connecting the compensator at the say midpoint, we will connect to the load side. Say this is the load and this is the sending end. Now the capacitor or the compensator, it is going to connect at load side. We are connecting the compensator. This is the compensator connecting the load side, and see what is the positive outcome from such type of connections. Okay, thank you.